Hello everyone, welcome to our fourth module on reinforced concrete. This lecture's topic is axially loaded members. Okay, let's start with what we mean by axially loaded members. Axially loaded members are actual structural elements that are in compression. The most commonly known compression member is the column. Columns are the vertical members which support floor loads transferred either vertically or through beams. In this picture, a sample of a vertical member, also known as the column, is shown. As I said, we name those members as columns in the construction industry. Before we move on to the engineering formulas for solving actually loaded members, we need to know that purely uniaxial loading is not permitted in design codes. The reason for that is based on the monolithic nature of reinforced concrete construction, and of course the possibility of lateral loads. Those lateral loads can be due to an earthquake or sometimes due to wind forces. Considering all those lateral forces, all members are subjected to flexural moments and shear forces in addition to axial loads. Now you know that uniaxial compression is not permitted in the design codes. You might be wondering, then why are we covering that subject? Well, the behavior and the strength of reinforced concrete members under uniaxial compression defines a limit case for combined flexure and compression. We will cover this very important concept in the upcoming modules. Let's go back and revise our knowledge in reinforced concrete. Now you know that we actually never use concrete without any reinforcement. Since the columns are also a reinforced concrete member, they are always reinforced by the longitudinal steel bars. We indicate the longitudinal reinforcement in the drawings like the dots going into the page. You can see this longitudinal reinforcement as I show them with the red dot here. Those longitudinal bars are used to avoid bending and settlement of the reinforced concrete members, and of course to decrease the time-dependent deformations in our structure. As you know from your daily life, columns can be in the shape of a rectangle or a circle. Of course, some of you might solve columns with odd shapes, but for now we'll focus our attention to only those two types. First thing we need to know is the reinforced concrete columns are designated by the type of lateral reinforcement to brace the longitudinal bars. In this picture, the column A is actually a tight column, where the column B is a spiral column. So this is the representation of a tight column, and this is a spiral column. Well, you might be wondering what is the difference between those two. The tight columns have the bars braced by the closed hoops, and spiral columns have the longitudinal bars wrapped with a closed space bar in the form of a spiral, as the name indicates. We need to understand the difference between a tight column and a spiral column because it will affect our calculations for computing the axial capacity of a vertical member. So this is an important concept. So let's go back into a little bit of history. One of the goals of the engineers and researchers in the early 20th century was to measure and compute the stresses in columns during the loading. However, they face difficulties for measuring the stress level at the loading stage. But one thing they learned from their tests was that the ultimate strength of an axially loaded column could be computed with reasonable accuracy. Researchers found that the ultimate capacity could be computed by summing the strength of concrete and the strength of the longitudinal steel. So you might be wondering, why are we adding up both the ultimate strength of concrete and the ultimate strength of steel at the same time? The answer is quite simple actually. In the case of uniaxial compression, steel may yield prior to concrete crushing, or concrete may crush prior to steel yielding. However, the column only fails if both concrete and steel reach their limiting values. Limiting values we are mentioning here is both of their ultimate strengths. Since we know that the failure of an axially loaded members happens only when both the concrete and steel reach their limit strengths, we are actually summing up their ultimate strengths. So before we move on to the formal expression of that summation, let's explore the difference between the tight and spiral columns regarding the uniaxial loading. So during the tests at the University of Illinois, it was observed that up to the maximum strength of the column, tight and spiral columns almost behaved identically, and the spiral added nothing to the strength. As you can see here, the behavior up to that point, the point I'm talking about is that point, the behavior up to that point is identical for tight and spiral column. By the way, this drawing shows the representation of a tight column and this one as the spiral column. Therefore, we can understand that the tight and spiral columns having the same cross sections and longitudinal steels, with longitudinal steel areas of course, behave identically up to that point, the point here. As you see, the behavior of the stress and the deformation is identical the same. At this point, crushing and spalling of concrete starts. In tight columns, this point is the point of ultimate capacity. For tight columns, beyond that point, the load carrying capacity of the member drops. A typical failure picture for a tight column is like this. The failure takes place by crushing of concrete along the two diagonals and buckling of longitudinal bars between the ties like this. So I will discuss the same thing for the spiral column, but I'm running out of time in this video, so see you on the part 2.